Another thing that iterated integration can be used for is for calculating areas. If the function inside the integral is equal to 1, then the integral of 1 dx dy, or dy dx, calculates the area of the region R. Let's look at an example of this. Let's let R be the region bounded above by the parabola y equals 4 minus x squared, and below by the line y equals x plus 2. And let's see if we can find the area. Let's start off with the sketch. Y equals 4 minus x squared is a standard parabola, which has been flipped upside down because of the minus sign and shifted 4 units upward. So it's going to have its vertex up here at 0, 4. And the parabola is going to be turned downward like this. We can also kind of easily see that when y equals 0, x is going to equal plus or minus 2. So the x-intercepts are going to be at negative 2 and positive 2. Y equals x plus 2 is going to be a line with slope 1 and y-intercept 2. So the y-intercept is going to be at 2, and the line has slope 1, which means that it comes through this way. Now, before I get too confident about where this is going to cross the x-axis, let's see. Well, in my sketch, it looks like it's going to be at negative 2. But let's actually confirm where those two curves cross. I can substitute y equals x plus 2 for the y up here to get x plus 2 equals 4 minus x squared. So basically setting the two equations equal. If I add x squared to both sides, I get x squared plus x plus 2 is 4. And I can subtract 4 from both sides to get x squared plus x minus 2 equals 0. That factors as x plus 2 times x minus 1. So indeed, one of the places they cross is when x equals negative 2, and the other place they cross is when x equals 1. So I can be a little bit more confident now that these two curves cross here when x is negative 2, and up here at some point whose x-coordinate is going to equal 1. If I want to get the y-coordinate of this point, I can plug into either of these two equations since the point lies on both curves. Notice that if I plug in x equals 1 into the parabola equation, I get y equals 3. And I get exactly the same thing if I plug x equals 1 into the equation for the line. So if R is the region which is bounded above by the parabola and below by the line, then this means that this part is the top curve and the line is the bottom curve. So R is going to be this region in between the two. So let me erase some of the extraneous parts so we can focus on the part that we're interested in. Now, when we decide how to set up the integral, we need to decide whether this region is vertically simple, horizontally simple, both, or possibly neither. I claim that this guy is not horizontally simple. Notice that if I draw a line passing through the region this way, horizontally, then it would enter on the parabola and exit on this line. Moving up a little bit, I'm still entering on the parabola and exiting on the line, but up here in the top, I'm entering on one part of the parabola and leaving on another part of the parabola. So if I were to try to integrate this going horizontally, I need to break it into two parts. One part where I'm going from parabola to line, and then this top part where I'm going from the left side of the parabola to the right side of the parabola. Let's see what happens if I send lines up through this region vertically. Over here, I would be entering on the line and exiting on the parabola. A little further over, entering on the line, exiting on the parabola. Over here, entering on the line, exiting on the parabola. So this is vertically simple. When I cut up through the region from the bottom to top, I'm always coming in along this line, and I'm always exiting the region on the parabola. So that's going to help us set up the integral. The bottom curve I can write as y equals x plus 2. And the top I can write as y equals 4 minus x squared. So when I set up my bounds, those become the inner bounds for y. I'm going to go from y equals x plus 2 to the top curve, y equals 4 minus x squared. So for a vertically simple region, notice that the top and the bottom bounds correspond to the top and bottom curves. On the outside, dx, I'm going to go from the smallest value of x in the region, which is -2, over to the largest value of x in the region, which is x equals 1. And then calculate area, then the integrand is just the function 1. Now, I'll just remind you that when you see a problem like this written in the book, they're probably not going to write the x equal and y equals. So you'll see it looking like this, and you'll rely on context to note that on the outside, I have x bounds, and on the inside, I have y bounds. I'm going to leave the y equals in, because I think it makes it easier to substitute. So, first of all, we're going to integrate 1 with respect to y, which is y, and they'll be taken from y equals x plus 2 to y equals 4 minus x squared. Plugging in the two endpoints and subtracting, I get, first of all, 4 minus x squared minus, plugging in the bottom, x plus 2 dx. Now this might look quite familiar to you. If you think back to the way that you calculated areas in Cal 2, then you took the top curve minus the bottom curve. And that's exactly what we've done here. We've taken the top curve minus the bottom curve. So let's simplify inside a little bit and then carry out the second integral. 4 minus 2 is 2, minus x squared minus x. And now integrating, I have 2x minus a third x cubed minus a half x squared taken from -2 to 1. Now I'll plug in my two endpoints and subtract. Plugging in 1, I have 2 minus a third minus a half minus, plugging in -2, -4 minus a third of -8 minus a half 4. And I'm running out of space here at the bottom. I'm going to ask you to trust me that this works out to 4 1/2, 9/2.